Two of the most famous subjects in math are modular forms and higher dimensional lattices. Both are extremely enticing if you love math, but they also may feel inaccessible. I wondered for a while how either of these topics are actually studied. Today, I want to demonstrate a use of modular forms to answer a question about the E8 lattice. This was my first taste of how the theory of modular forms can be used in practice, and the connection between the E8 lattice and modular forms is incredibly interesting. First, let me introduce the problem by talking about lattices. A very simple example is points on a grid. The corners of the tiles on a chessboard form a part of a lattice. So long as we continue this pattern of points for infinity, we have a true example of a lattice. To be clear, the actual lattice is only these points in the plane, not the grid or the tiles. A lattice has no length or area and is only a collection of points, or vectors. This lattice also doesn't need to be as nice as it is. We could skew all of the points or space them, and we still have a valid lattice. Here's one interesting way to arrange them. Notice that this represents centers of cells in a honeycomb. It also happens to be the densest way to pack 2D spheres, which is circles. As it turns out, some of the most interesting lattices have the densest sphere packing for their number of dimensions. So yes, there are also lattices in other numbers of dimensions. In 3 dimensions, there are a lot of simple lattices which look like what we would call crystals in 3D. In fact, the grid from earlier, or this 3D lattice, is a combination of copies of one of the simplest we could consider. The grid is a combination of 2 copies of the integers. Yes, the integers are also a lattice. It's time that we give a rigorous definition of what exactly one is. So a lattice is a discrete set of points within a vector space that, like a vector space, is closed under addition. You can add 2 points in it, and it'll always end up still within the lattice. One thing we can do with lattices is find their dual using linear algebra. I have linked a paper that discusses this in more depth. In essence, the dual lattice contains all of the points that have an integer dot product with any point from the original lattice. You can project any point from the dual onto any point from the original and get an integer length. It is clear that the integers are self-dual. If I multiply 2 integers, the result is always an integer. That means that the dual lattice of the integers is itself. This is an incredibly special property of a lattice, and we say the integers are unimodular, since they are self-dual. This is not true in general. Take the even integers, for instance. They are a lattice, but the dual lattice is all of the half integers. So already, scaling a lattice will break this self-duality if it has it in the first place. Or take the hexagonal lattice, which isn't self-dual at any scale. To show this Catan board again, the dual lattice is all of the centers of the hexagons and all of the intersections where you place settlements. So the dual lattice is similar, but it's also rotated, so that the lattice isn't self-dual at any scale. However, both the integers and the hexagonal lattice can be what are called even lattices if scaled properly. Even lattices are those where all of the vectors have an even norm. The norm is just the square of the magnitude or length of the vectors. It is essentially the number you get if you apply the Pythagorean theorem for the length, but then you don't apply the square root. Of course, all of the even integers have even norms, so that lattice is even. We could fine-tune the integers to be either unimodular or even, but we clearly could not achieve both at the same time. It would be special then if a lattice had both of these properties simultaneously. In fact, there are no even unimodular lattices until dimension 8. The first even unimodular lattice is the E8 lattice. This lattice is pretty much impossible to accurately visualize. One example is that it has 240 vectors with the smallest non-zero norm. In the hexagonal lattice, this number is 6. The central question of this video is, how do we count how many points on the E8 lattice have a certain norm? To solve this problem, we will introduce a special type of function that gets associated to any given lattice. That's the lattice's theta function. Take the sequence of how many vectors are at each norm for the lattice. So for instance, how many vectors have a norm 0, 1, 2, 3, and so forth? If you take this sequence of numbers, you can construct a generating function that has these numbers as the coefficients. That way, we can trade questions about lattices for questions about functions. The type of function we will use is the same as the type of function for a modular form. These are not real input to real output functions like the ones studied in first semester calculus. This is a strange function type, but it maps from the upper half of the complex plane to the entirety of the complex numbers. Normally, we call the input of this function tau, a complex number with a positive imaginary part. The generating function that we will use is called a Q expansion. It looks like a power series of the variable Q, but Q is a substitution for tau by the relation Q equals e to the 2 pi I tau. Since tau lived in the upper half plane, Q is then a point on the unit disk, and a Q expansion is really a type of Fourier series. However, if you know very little about Fourier series or complex analysis, don't worry, I won't go into depth on these topics. We are also going to do something a little strange with the generating function. We are going to take the number of vectors with some norm and match it to the term with Q to the power of half the norm. This is weird because you would assume we would match the norm with the power. I think this will become clear later as things fall into place pretty nicely, but it does look strange. For that reason, I will show an example using an even lattice where all the powers will remain integers. The even integers have a really simple theta function. There is one integer of norm 0, which is 0. So this theta function has a constant term of 1. For the rest of the integers, their absolute values are integers, so the norm of any integer is a perfect square. Plus, whenever there's a positive integer with some norm, there will also be a negative integer with the same norm. So we will fill out the rest of the terms like so. Then, if you want to know how many vectors have a norm of 16, you would look to the coefficient of the term with a power of half 16. So look at the coefficient of the q to the 8 term. Its coefficient is 2. So there are 2 vectors with a norm of 16 in the even integers. This is because there are 2 even integers with absolute value of 4. This is the whole thing in some notation. With the integers, the theta function hasn't helped us solve the counting problem, but this will help for counting on the E8 lattice. As it turns out, the theta function of an even unimodular lattice, like the E8, is always a modular form. For the rest of the video, I will show how to solve for the E8's theta function. As I mentioned, modular forms are functions from the upper half plane to the complex numbers as a whole. Often graphs of modular forms are presented like this, where colors represent the complex output, and all inputs in the upper half plane are mapped to a color. These functions also have a complex analytic niceness, as they are said to be holomorphic everywhere, including at infinity. This essentially means that they are complex differentiable everywhere. A modular form also equivalently must have a Q expansion, like the theta functions. So what is a modular form? Modular forms transform nicely under a change of the domain, similarly to how a sine wave transforms nicely when its domain is shifted by multiples of 2 pi. The modular forms aren't necessarily invariant under their transformation of domain, just predictable. The transformation for the domain of the modular form is called the action of the modular group. The modular group is any integers a, b, c, and d such that ad minus bc equals 1. And the action of the modular group is taking tau to a times tau plus b over c times tau plus d. Many of you will notice that we can express this as the set of all 2x2 matrices with integer entries and determinant 1. However, the action of it is on the complex upper half plane. From now on, I will only be discussing level 1 modular forms, which transform nicely under the full modular group. There are other modular forms which only transform under a subgroup. The definition of a modular form for the full group allows you to take any member of the modular group, and a relation will hold if you act on the domain of the modular form by that element of the modular group. It is almost invariant under the modular group, but when the action is performed, the new function is the original function times a new fudge factor. This factor is c times tau plus d all to the k. As you can see, we have now introduced some new variable called k. This is the weight of the modular form, and we can tune this to discuss modular forms of different weights. You can see too that a special case is k equals 0, because these weight 0 modular forms are actually just invariant under the action of the modular group. As it turns out though, the modular group is generated by just two transformations, which can combine to form any element of the group. These are often known as S and T, and niceness under S and T is all that is needed to be shown for niceness under the full modular group. T is very straightforward, and it takes tau to tau plus 1. Modular forms are invariant under T, which is shown by being periodic left to right. S takes tau to minus 1 over tau, and its equation looks like this. This is typically more difficult to prove. Take our theta functions, for instance. They are definitely invariant under the action of T, because they have a Q expansion. Any term in the Q expansion will be rotated around to its original point when an integer is added to tau. In the case of the E8's theta function, we would need to prove niceness under S to prove that it's a modular form. So how do we do that? The answer comes from something called the Poisson summation formula. The normal formula says that summing a wave over integer positions is equal to summing its frequency distribution over integer frequencies. That is, you can sum over the function's values at integers, or you can take the Fourier transform of the function and then sum the values of that over integers. And these results will be the exact same. Now, this actually works the way it does because the integers are self-dual. So if you take any unimodular lattice in any number of dimensions and sum over that instead, this formula still holds because that lattice is self-dual. In this case, you are summing a distribution over positions in a vector space and then doing the same in the momentum space. Therefore, this formula works over a unimodular lattice like the E8. Since the theta function can be viewed as a certain sum over the E8 lattice, this formula can be applied, and this is the end result. There's an excellent derivation of this formula on MIT's website for those who are curious, but I felt that it reached beyond the scope of this video. If we take this identity, though, it looks a lot like the modular form condition for the S transformation, but there's this extra square root of I in there. With the E8 lattice, though, this is taken to the power of 8. So since the square root of I is an 8th root of unity, this just becomes 1. And there, we now know the equation for niceness under S is satisfied. So we know two things. The E8 lattice has a theta function that's a modular form for the full modular group. We know this because we already showed that all of the theta functions satisfy the T equation. And now we know that this function also satisfies the S equation. Additionally, the weight of this modular form is half the dimension of the lattice. This is an amazing revelation, and we now know something rich about the E8's theta function. It's a modular form of weight 4, but here is the magic. With that information alone, we immediately know exactly what that theta function is. Since we know the theta function is a modular form, it would be good to know some examples of modular forms. The non-trivial example of a modular form is 0. 0 is special though because it's a modular form of every weight. This makes sense too, because modular forms of the same weight sum to another modular form of that weight. So if we were to subtract a modular form from itself, we should get 0, and that should also still be a modular form of the same weight. Also, any multiplying by a constant yields a modular form of the same weight. The proof of these facts aren't too difficult. Now, these criteria sound a lot like a vector space. We have a 0 element, we have closed addition, we have scalar multiplication. That's because the modular forms of a certain weight are a vector space. To be more specific, they are a complex vector space. We're now looking for basis modular forms to span these vector spaces. We don't just have to look for random examples of modular forms of different weights. We can exactly define the entire space by finding its bases. This is exactly the property we will take advantage of to determine the theta function for the E8 lattice. So let's start by looking at weight 0 modular forms. They're invariant under the action of the modular group. It's clear that any constants would be invariant under this action, so the constants are all weight 0 modular forms. But it turns out they are the only weight 0 modular forms. So we can define the weight 0 modular forms as the span of just one constant function. In other words, the weight 0 modular forms are a one-dimensional, complex space. In general, though, our modular forms are not going to be this simple. For modular forms of the full group, every weight has two components that combine. One is all of the complex multiples of something called an Eisenstein series, if it exists for that weight. The Eisenstein series is essentially a manufactured modular form. It's an infinite series that is designed to be a modular form, and it's easy to construct for different weights. The other component of the weight k modular forms are the non-Eisenstein series modular forms called cusp forms. Not all weights have cusp forms, and in fact there are no non-zero cusp forms until weight 12 and greater. So let's look at the Eisenstein series. It is a sum over pairs of integers mn. It is essentially designed such that a factor of c times tau plus d to the k pops out under action of the modular group. And that's something that is not terribly difficult to prove if you notice how this function transforms under the action of the modular group. However, notice what happens when k is odd. When this is true, the Eisenstein series has all of its terms cancel. Therefore, the Eisenstein series is just 0 for odd weights. Okay, now our goal is to determine the space of weight 4 modular forms in hopes of being able to find the E8's theta function. There's an Eisenstein series for weight 4 that both converges and is not 0. But again, there's no cusp forms until weight 12. So just like for weight 0, the weight 4 modular forms are a one-dimensional vector space. Now we know all the weight 4 modular forms. They are simply all of the complex multiples of the weight 4 Eisenstein series, which we will call G4 of tau. Putting all of this together, we know that the theta function of the E8 lattice must be a multiple of this series. We know the non-normalized series has a constant term of 2 times zeta of 4, but the E8's theta function must have a constant of 1 since there is only one norm 0 vector. Therefore, the theta function must be G4 over 2 times zeta of 4. We still have not answered the question of how to count on the lattice, but we are very close now. Here's an identity for the weight 4 Eisenstein series. This sigma 3 of n is called the third divisor function of n. In this function, you sum all the cubes of divisors of n. We now know that the nth coefficient of our function must be 240 times the third divisor function of n. I won't prove this identity now, but on the screen I have put two identities that are often used to derive this fact if you differentiate some things a couple times. Now there's a clear way to compute how many vectors of a certain norm there are. We can now show that there are 240 vectors of norm 2. The number of vectors of norm 2n is 240 times sigma 3 of n. So if n equals 1, the number of vectors of norm 2 is 240 times sigma 3 of 1. The divisors of 1 are just 1, so the sum of cubes of divisors is just 1. Therefore, there are 240 vectors of norm 2 in the E8 lattice. We can do this again with the next possible norm, which is norm 4. In this case, we have a norm of 2n equals 4. So n equals 2, and the number of vectors is 240 times sigma 3 of 2. Sigma 3 of 2 equals 1 cubed plus 2 cubed equals 9. So there are 240 times 9 equals 2,160 vectors of norm 4. I have certainly opened up a lot of unanswered questions in the course of this solution, but I think that's great for two reasons. This is a pretty accessible description of a modular forms problem, which is something that's hard to come by, and it shows a clear application of the subject from start to finish. The second reason is that there are now several problems in modular forms you may be interested in working on yourself that are needed to prove the solution fully. Here are some on the screen. These are all pretty great exercises in modular forms, but as a warning, I have found that all roads lead to a complex analysis textbook. One thing you should know is that all even unimodular lattices have a theta function that is a modular form of level 1. So for instance, the even more interesting Leech lattice has a weight 12 modular form as its theta function, since the Leech lattice lives in 24 dimensions. So there are more connections between lattices and modular forms than just the E8 lattice. Understanding the Poisson summation formula generalizes this fact for all even unimodular lattices. To me, it's incredibly interesting that these strangely defined functions are somehow so important that they can answer questions about some of the most beautiful geometric objects in mathematics.